Hello, good day again. Welcome again to CE 3 to 11 Principles of Steel Design. So for this pre-recorded lecture, we would be discussing about the analysis and design of compression members. Okay, but if you can remember during our first pre-recorded lecture that whenever we are to design a certain structural member, the first thing that we should take into consideration is the manner in what way or the manner in which a certain structural member will fail. And once that you have known already in what manner that certain structural member will fail, you must design that certain structural member in a way that it wouldn't fail in the manner that you have anticipated. So, paulit-ulit tayo doon. And if you can remember during that pre-recorded lecture, na kapag magsasubject tayo ng isang compression member, ang tendency niya is to buckle. So, in this pre-recorded lecture, that would be our topic. So if we are to talk about compression members, this is the most common failures of it. So the first one would be through flexural buckling. The second one would be through torsional buckling. And the third one would be the combination of both flexural and torsional buckling, which is flexural torsional buckling. Okay, so ano ba tong flexural buckling na to? It would be simple, magbe-bend lang siya along an axis. So, let's have an example na lang, no? So, eto. So, for example, that this is to be your structural member. And if you are to subject this structural member with a compression force, or, a compressive load. So, yung load natin dito and dito. So, the tendency of failure, so yung failure natin would be like this. So, as you can see, nagbabakal siya along the weak axis. So, by the way, meron pala tayong strong and weak axis. Nasaan ba yung open board? Okay. So, if you can see here, meron tayong x and y axis ng cross-section natin. And it would buckle along the weak axis. Kasi pag strong axis, hindi siya magbabuckle right away kasi ganito siya. Okay, balik tayo sa mukha ko. If this is to be, once again, your structural member, meron tayong X and Y axis dyan. So, ewan ko kung nakikita nyo. So, if you are to subject this structural member right here with a certain force, magbabuckle siya along this axis only. Doon lang sa mahina. Hindi mo siya maibuckle ng paganto. So, yung magsag siya ng paganto, hindi mo magawa yon. It's because that this axis right here is stronger than that of this. Once again, if you are to subject this with a force, ganyan yung failure niya. So that is for flexural buckling. So along the weak axis. And dito, ang weak axis natin is the y-axis kasi kung ito man yung ating axis, ulitin natin. So if this is to be y and this is to be x, etong moment of inertia natin dito would be greater than its moment of inertia here. Kahit i-check nyo pa yung table or kahit i-check nyo pa ang ating inertias. Okay, so that is for flexural buckling. But what if the inertias of both sides, paano kung kunwari yung Ix is equal to Iy? So the common failure of that would be the torsional buckling. So as you can see here, this would be a cross. And by inspection, malalaman nyo na same ang Ix and Iy natin. So the inertia X and the inertia Y. So if that would be the case, ang mangyayari dito sa certain structural member natin na to is to buckle torsionally. So ibig sabihin magti-twist siya. So I cannot give you an example using this ruler. Pero subukan lang natin. Okay, so if this is to be our ruler, magti-twist siyang paganto. Pero hindi nyo nakita. Kaya wag na lang. Okay, so balik tayo dito. So once again, if your member would be having identical inertias in both major axes, the most common failure of it would be torsional buckling. So that is for letter B. And as for letter C, that would basically be the combination of both. To give you an example, it would be like this. So sa flexural buckling natin, if you are to subject this certain structural member by a compressive load, this is the bending through the major axis. Ito yung hindi ko may pakita sa inyo kanina kasi hindi ko mai-bend yung ruler along its major axis. And this is the flexural buckling through the minor axis. So this is the most common failure kasi Etong minor axis natin mas madalas is yung mas mahina na axis. So it would bend that way instead of this way. And for torsional buckling, it would twist. And as for the flexural torsional buckling, ito yung combination ng both. So it would be bending flexurally and it would buckle torsionally. So this would be its failure. Yung parang kunwari may kiliti kayo sa leeg tapos biglang may bumubulong sa inyo. So yun yung tinatawag na flexural torsional buckling. Hindi ko pala naisabi sa inyo during our meetings before that ang basis natin dito is the R. So yung R natin na pinag-solve nyo for the slenderness ratio. And R is actually equal to the radius of gyration. So, ayan ang ating radius of gyration. And for us to solve for the radius of gyration, that would be the square root of the inertia divided by the cross-sectional area. And from that, if we are to solve for the radius of gyration in the x-axis or in the strong axis, that is to be Ix over A. So, from that also, Ry is equal to the square root of Iy over A. And using your knowledge that you have gathered during your statics of rigid bodies lessons, I mean, that SEM, etong Iy natin is equal to the inertia. Kung ano man yung inertia nyo, hindi ko lang kung bakit ko pa sinulat tong araw na to. Pero inertia plus yung transfer formula kung kakailanganin nyo ng ating transfer formula. So that is how you would be solving the radius of gyration. And ito yung basihan natin ng ating mga strengths sa ating columns or sa ating compression members. So, dito sa mga to. Okay, so this would be the tables that we would be using in the design and analysis of compression members. So, this would be table 5.1. Nakalimutan ko kung anong page to ng inyong book. So, ilagay ko na lang sa description kung anong page to. But this is to be table 5.1 by McCormac. So, dun sa librong yon. And actually, this is also in the National Structural Code of the Philippines and in the AISC. So, pare-pareha silang tatlo. So, that this is to be the approximate values of effective length factor K. And as you can remember in the slenderness ratio, di ba ito yung slenderness ratio natin, which is KL over R. And this K right here is this, kung itong K na to. And yung L is yung length mo and yung R is yung radius of gyration mo. So this is to be the first table that we would be needing in this subject, I mean in this lesson. And this would be the formulas for you to memorize here. So this is from NSCP, so National Structural Code of the Philippines. So this is to be formula 505.3-1. So once again, halimutan ko yung page nito, ilagay ko na lang sa description ng ating classwork. Okay. And ito, alam nyo na to, this would be another table that we should be using. So ito yung ating mga yield stress and itong mga tensile stress. But in compression members, we wouldn't be using this tensile stress. Because if you can see here, if your member is to be buckled, hindi naman siya nag-rupture. Nag-yield siya kasi nag-elongate lang yung mga fibers niya pero hindi naman siya napunit. So with that being said, we would only be using the yield stress in this topic. So sa itong yield stress lang gagamitin natin. Okay, and so for your sections, you can use the Strength of Materials book by Ferdinand Singer. And you can also use the AISC Shapes database, yung Excel file ng AISC for you to choose your sections. Okay, so what would be our steps in analyzing your compression members? So just like your other analysis problems, the first thing that you should do is to list the parameters or the properties needed. So step 1 is to list the properties. So what are these properties that we would be needing in solving for our, in analyzing our compression members. So the first property that we should know is the length. So kung ano ba yung haba ng ating compression member. And another thing, we should also know the yield stress, so Fy, and we can get this Fy right here in this table right here by ASTM. So it would be in this column only. So as for the tensile stress, itong Fu natin, hindi natin kailangan yan in buckling because hindi naman siya mag-rupture kapag mag-buckle siya. So it would only yield. Okay, so Fy lang, hindi na natin kailangan yung Fu. So after that, we would also be needing the section properties. So section properties. So how can we get that section properties right there? So we would be getting it from this book by Ferdinand Singer or through the AISC Shapes database. So yung Excel file. Or if you have a book na AISC, you can also get it from there. Okay, so ano ba yung mga kailangan nating parameters? So the first parameter that we should need is the cross-sectional area. And after that, we should also get the inertia about the x-axis and the inertia about y-axis. And after that, we should also know the radius of gyration about the x-axis and the radius of gyration about the y-axis. Kasi compare natin sila kung ano yung mas matibay and kung ano yung magbabakal. For pretend that you cannot see these parameters right here in this database right here, you can actually solve for them. So as for the inertia, parang sabi ko kanina, napag-aralan nyo yan sa statics of rigid bodies nyo. And as for your Rx, so R is equal to square root of I over A. Once again, so ayan siya. So ayan ang ating step 1. So for step 2, ang gagawin natin dyan is to determine the effective length. So determine the effective length. Okay, so paano natin makuha yung effective length na yan? We would be using this particular table right here. So, eto siya. So, ito yung gagamitin nating table. So, what does this mean? So, if you can see here, if this is to be your case, kunwari, yung dalawang ends nyo would be fixed. So, this is to be a fixed support and this is to be a fixed support. Ang effective length natin would just be half the length. So, what does that mean? So, this length right here is the only one to be experiencing buckling. Kasi nga fixed support siya dyan, yung dito sa sides natin na to, parang stiff siya and hindi siya magbabuckle. So, our effective length right there would just be 50% of the whole length. Thus, its theoretical K value would be 0.5. By the way, ang effective length natin would be this KL right here. So, KL, this is to be the effective length. So, meaning yan lang yung ating may consider for buckling. So, if this is to be your case once again, etong length na to is just 50% of the whole length, thus its theoretical K value would be 0.5. And if this is to be the case, so if for example that your member is fixed on one side and in one side it is only pinned or naka-hinge lang siya, it would buckle this way and the effective length of this, of the buckling proper itself, is just to be 70%. Thus, 0.7 yung ating K value. And as for C, so for example that your member here would be fixed and yung dito natin would just be fixed nga siya for rotation pero translationally free siya. So itong case na to, your value would be 1. So meaning this whole length right here would be subjected to buckling, so 100%. So this is to be the parameters that we would be needing. But once again, this would just be the theoretical value. But if you are to design certain structural members, we would be using these factors instead para may factor of safety tayo. So for example, that you would be designing a certain structural member in this case, instead of using 0.5, you would be using 0.65. So Ito kasi ang ating recommended design value with, of course, factors of safety. And if you would be multiplying this by the length, that would be the effective length itself. So, dito. So, this is to be K times L. So, that is to be your effective length. Okay, so now that we have our effective length already, the next thing that we should do is to solve for the slenderness ratio. So, solve slenderness. Ratio. And how can we solve that? Slenderness ratio is equal to KL over R. So, itong KL natin would be the effective length. So, basically, that is just the effective length divided by the radius of gyration. Okay, so after we have solved for that already, so our next step is to solve for the elastic critical stress. So, elastic crit. And how can we solve for that elastic critical stress right there? It would be this certain formula right here. So, ito siya. And if you can see here, ito siya. Your elastic critical buckling stress is equal to pi squared E over slenderness ratio squared. Then as for E, that is to be your modulus of elasticity, and in most cases, our modulus of elasticity would be 200 gigapascal for steel. So that is to be 200,000 megapascal. So it would depend on the problem, but that would be the most common value for our modulus of elasticity. So yan, Fe. So solve for Fe. Then for number 5, solve for the flexural buckling stress. So flexural buckling stress. And how can we solve for that? We would still be needing these formulas right here. So etong page na to ng ating National Structural Code of the Philippines. And ito yung mga formulas natin for FCR. So by the way, this is to be FCR. So, ayan ang ating flexural buckling stress. So, if you can see here, meron tayong dalawang cases, ano? So, if you are to compare your slenderness ratio to this value right here, 4.71 times the square root of E over Fy, kung nag-fall dito yung inyong slenderness ratio, you would be solving for FCR, by this formula. So, FCR is equal to 0.658 raised to Fy over Fe times Fy. And if your slenderness ratio is larger than this, that is to be FCR is equal to 0.877 Fe. And yung Fe natin is this. Pwede din natin i-check ito. Or Fe is greater than or equal to 0.44 Fy. Test dito din. Fe is less than 0.44 Fy. And if you already have your value for FCR, you can actually get the value of Pn. So the nominal stress is equal to, the nominal load is equal to Ag times FCR. Okay, so that would be your nominal load for your analysis problem. And after that, so for number 7, apply these factors of safety or the reduction factor via LRFD or ASD. So, ayan dalawa. And as for your value of phi for LRFD, that is to be 0.9. And the value of omega in ASD is 1.67. So, bakit ito yung gagamitin natin? It's because that we are analyzing your structure in yielding. So, 0.9 and 1.67, kung naalala nyo sa tension members nyo, that is to be the factors of safety and the reduction factor for yield. That is the steps in analysis. So, paano naman sa design? So, medyo pabaliktad tayo dito. And just like in your design of tension members, the first thing that you should do is to determine the load combinations. So load combinations. And alam nyo na itong load combinations nyo. And the second step is, so kung ano ba yung ginawa natin dito? So nag-solve tayo ng effective length, ng slenderness ratio, and whatnot. So dito naman sa ating design, so palitan natin para may visual representation kayo. So for number 1, this is to be load combinations. And for number 2, the second step is for you to assume your KL over R. So assume KL over R. And kapag mag-assume kayo ng KL over R, it is better for you to assume KL over R to be 50. So ang magandang range kasi ng slenderness ratio natin for compression members, that is to be 40 to 60. So let's just get the average and assume KL over R. So after this, you would be having two methods actually. So meron tayong method 1. Lagyan natin dito. So dito yung method 1 natin. So after step 2 na to, no? And this is to be method 2. So you have two methods in designing your compression members. Okay, so for member 1, palitan ulit natin yung color. So yellow na lang tayo dito. So for step 3, after you have assumed this already, KL over R, you can now actually solve for FCR. So FCR is equal to, ito yung gagamitin nating formula, itong nasa una. So we would be assuming that your slenderness ratio is less than or equal to this parameter right here. So 0.658 Fy over Fe times Fy. And after that, so for your step 4, you can now solve for the required gross area, which is Ag is equal to Pu over Phi FCR. So that is for LRFD. So for ASD, check nyo na lang sa ASD, that is to be omega Pu over FCR. Okay, so I mean PA sa allowable stress. But in designing your compression members, it is better for you to solve for the cross-sectional area as brought about by LRFD. So LRFD lang gamitin nyo sa pagkuha. But in the analysis part, you would be checking the adequacy of it in ASD. Okay, so after you have figured out what your required cross-sectional area is, so the next step is to select trial section. So that is to be it. So sa step 5 natin, babalik tayo dito sa ating database. So i-check nyo dyan kung anong cross-sectional area. I mean kung anong section yung merong cross-sectional area ng hinahanap nyo. And after you have selected your trial section, the next step is to analyze using these steps right here. So i-check nyo kung yung napili yung cross-sectional area would be adequate to carry your load combination. And if you are in the analysis part already, you would be doing the LRFD and ASD. So kasi pag dito sa design, LRFD nga lang yung pagkuha natin ng section para hindi masayang ang oras nyo. Okay, so for method 2, bakit methods nakalagay dito? So palitan natin to, method 2. So as for method 2, ito medyo simple lang din ito. So ano bang magandang color dito? Red naman. So the step 3, so after steps 1 and 2, and kapag method 2 na, ito na yung ating method Step 3, I should say. Okay, the next thing that we should do kapag method 2 yung gagawin natin is to solve for r. How can we solve for r? So if you can remember here that we have assumed your KL over R, or slenderness ratio, equal to 50. So for us to solve for R, and diba, KL over R is equal to 50. So from that, R is equal to KL over 50. And after you have solved for the value of R, you would be using your R to select your sections right here. So dito sa ating um, database na to. So for example, nasa ba yung database ko? Okay, so for example that this is to be your database, hahanapin mo lang dito sa inyong table yung mga values ng R. So in this case, it would be this, and asan yung isang R, Rx, and Ry, this. So highlight natin yan. You would be selecting the minimum R right here, kung ano yung patok sa inyong panlasa, joke lang, sa inyong na-design. Okay, so with that being said, your step 4 would now be, to select trial section. So yun yung ginawa natin earlier. Select trial section with the property of your R. And after you have selected your trial section, the last step is to analyze your trial section if it can carry your load combinations. And once again, in this step right here, you would be solving for both ASD and LRFD. So, ayan. So, this would be the steps in designing your compression members. Okay, so let's just have an example instead. Okay, so for our illustrative example, determine the LRFD design strength and ASD allowable strength of the column shown. So this would be your column. Its length would be 3.5 meters. So itong L niya is 3.5 meters. Pinned at one end. So ito, nakapin daw siya dito. And fixed at the other end. So ito din siya. In both axes. So this would be your X and your Y axis. So, nakaganyan siya. In some cases kasi, meron yung mga steel connections natin na sa X-axis niya, ganito yung setup, pero yung sa Y-axis niya, iba. Like, fixed yung dalawang support. So, for example, ganun siya. So, pero dito naman, sinabi niya na pinned at one end and fixed at the other end in both axes. So, X and Y, ganyan siya. And the section that we would be using is of W12 by 50, then A992 steel. Okay, so let's start. So if you can remember earlier, our step 1 is to list the properties. So list the properties. Okay, so ano yung mga kailangan natin properties? That would be the L. So our L would be 3.5 meters. And what would be our yield stress? So for yield stress, we would be using A992 steel. And if we are to use A992 steel, so check natin dito, sabi yung A992, it would be this. And this would be its yield stress. And ang gamitin na lang natin dito would be 50. So its yield stress would be 50 KSI. So let's just convert this right away to megapascal. So just multiply this by our conversion factor of 6.895. So ano na yung sagot natin dyan? So that is to be 50 times 6.895. That is to be 345 megapascals. So 345 megapascals. Okay, so that would be our Fy. So ano pa yung kailangan natin? So section properties. So section properties. Okay, since ang gagamitin natin dito would be W12 by 50, so we would be going to our Excel file. So it would be this. So W12 by 50. So hanapin natin siya dito. But in my case, I would be typing Control F, tapos hanapin ko W12 by 50. So hindi ko alam kung nakikita nyo, pero hindi ata. So W12 by 50. And nandito siya. Ito yung aking hinanap na W12 by 50. So I would just be highlighting it para makita nyo. So ang mga kailangan ko kasi dito would be the areas and the radius of gyration. So pwede mo din kunin yung inertias natin para sure, pero sa nakikita ko naman dito, mukhang hindi pa natin kailangan. Pero para sure, ilista nyo na lang. Okay, as for the area, since this is to be in English, kasi W12 by 50, posible namang naka-metric yan. And yun, since that would be in English, so yung area natin na ito, so read natin yan. This is to be the area, and that is to be in square inches. And as for the radius of gyration, nasan ba yung radius of gyration dito? Napin natin. Okay, hindi ko makita. Yun, ito pala. Yung highlight pala natin kanina. So, that would be these intersections right here. So, I would be changing that. So, ito, this is to be in inches and this is also to be in inches. Kung nalilito kayo doon, punta kayo dun sa first tab, which is yung readme, then i-check nyo yung, basahin nyo na lang to para maintindihan nyo yun. So, those would be the parameters that I would be listing. So, balik tayo sa ating open board. Oops, mukha ko yan. Open board pala. Ito pala. Okay, so as for the section properties, AG is equal to, nakalimutan ko. AG is to be equal to 14.6. So that is to be 14.6 square inches. So 14.6 square inches. Rx and Ry, that is to be 5.18 and 1.96. So, ito. 5.18 and 1.96. So, both are in inches. And since we are in the Philippines and we are to use metric system, let's just convert this into millimeters. So, I would be multiplying this by 25.4. So, 25.4 mm divided by 1 inch squared. So, ganun din dito, times 25.4 times 25.4. Okay, so solving for those, ang AG natin would be 14.6 times 25.4 squared. So, times 25.4 once again, that is to be 9419.336. So, that is to be 9419.336. So, millimeters squared. And as for our Rx, that is to be 5.18 times 25.4. So that is to be 131.572. So 131.572 millimeters. And as for our Ry natin would be 1.96 times 25.4. That is to be 49.784. 49.784 millimeters. So those would be our section properties that we would be needing in this analysis proper itself. So once again, if your section would be built up, kung kunwari dalawang channels and doon naman sa ating specification ng AISC, walang channels doon, ang kukunin nyo doon actually is the inertias. So, ito, lagyan ko lang ng note. So, if your section is to be a built-up section or if wala dun sa ating database ang inyong property na sinosolve, so, get the inertias of each, so Ix and Iy. And of course, the Ag, get the values of Rx and Ry using the formula that I have shown to you a while back. So, ayun siya. Okay, so, sinolve na natin ngayon ng ating section properties in metric. But disclaimer, actually nagpakahirap lang ako kasi meron naman talaga siya dito. So if this is to be our section, W12 by 50, if you would be scrolling to the right by, let's say, this much, hanggang makita nyo itong nomenclature ulit, this would be its metric counterpart. So this is to be the area, and this is to be the Rx and Ry. So Rx and Ry, respectively, in metric. So nakita nyo din, 49.8, 132, and 9420. And if you can see our board right here, basically, same siya. So, nagkatalo lang sa decimal points. Pero, pinahirapan ko lang sarili ko. Okay, so I would now be using these section properties in solving for our friend right here. Etong friend nating column na to. Okay, so from that, what would be our next step? So, the next step, so for number 2, our next step right here is to get the effective length. So, effective length. Okay, how can we get the effective length? Once again, that is to be K times length. So KL. And RL is actually equal to 3.5 meters and RK, di pa natin alam, pero masasolve natin yan. Okay, so for RK, it is said here that it is pinned at one end and fixed at the other end in both axes. So pinned and fixed. So from that, we would be checking this table right here. Kung ano ba siya. So, pinned and fixed. So, alin ba siya dito? So, that would be case B. Pinned here and fixed here. Though it would be having a theoretical K value of 0.7, we would be using 0.8 para meron tayong factor of safety. So, that would be the recommended design value. Okay, so from that, so na tayo. Okay. This is to be, yung K times L natin would be 0.8 times length, and our length once again is 3.5 meters. So that is to be 3,500 mm. So our effective length would now be 0.8 times 3,500, so 2,800 mm. So meaning ito lang yung length na magsasubject sa buckling. Okay, so what would be the next? Oh, by the way, this is true for both x and y axis. So, ito yung k and l mo for both x and y. Kasi same lang daw siya. Okay, so for number 3, so what would be the next step? The next step is for us to solve for the slenderness ratio. So, slenderness ratio. And what would be our slenderness ratio once again? That would be KL over R. So for our x-axis, that is to be KL, which is 2,800 mm, divided by, ano yung Rx natin? That is to be 131.572. So solving for this, the slenderness ratio about the x-axis would be, so 21.281. Okay, so that would be the slenderness ratio for our first. So, sa x-axis natin. What about for the y-axis? So, for the y-axis, that is to be 2,800 divided by, what would be our ry? That would be 49.784. So, 49.784. So, let's say 49.78 na lang. So, this is to be 56.247. So, 56.247. Okay, so this would be your slenderness ratios for both x and y axis. So, ano ba yung pipiliin natin dyan? We would be getting the larger value kasi if we are to speak about slenderness ratio, the higher its value, the more slender it is. And the more slender it is, the more it is susceptible to buckling. This is to be more critical in buckling. So ito yung gagamitin natin for the next couple of steps. So now that we already know our slenderness ratio, so ito check na natin to. Ito yung gagamitin natin, governs. So for step 4, ano na yung step 4 natin kanina? We are to solve for the elastic critical stress. So ito. So Fe is equal to pi squared E over slenderness ratio squared. So KL over R squared. Okay, so to solve for that, that is to be equal to, so equal to pi squared times E, and the modulus of elasticity for steel would be 200 gigapascals, or that is to be 200,000 megapascals. That is to be for the value of E. So we would be dividing this by KL over R squared. And our slenderness ratio, KL over R, is to be 56.247. So lagay natin dito, 56.247 squared. Okay, so solving for this, ang magiging sagot natin for Fe would be pi times 200,000 divided by 56.247 squared. May mali pala. Nakalimutan kong i-square ang ating pi. So, pi squared times 200,000 divided by 56.247 squared. So, our answer here would be 623.923. So, 623.923 megapascal. So, this would be our value for Fe. So, for step 5, next slide na tayo at medyo napupuno na for next slide. So, for our step 5, we would be computing for the flexural buckling stress. So, that is to be FCR. So, if you can remember in our previous table, ito pala, itong formula natin, this would be the values of FCR. So, ito yung FCR natin, and ito din yung FCR natin na pangalawa. So, para malaman natin kung anong formula ang gagamitin natin, we must compare our slenderness ratio to this value right here, which is 4.71 times the square root of E over Fy. And kung ano man, kung if it is less than or equal to that value right there, you would be using this formula. And if it is greater than this value right here, you would be using this formula. So 4.71 square root of EFY. Okay, so substituting known values, this is to be 4.71 times the square root of E. So what would be our value of E? That is to be 200,000 megapascals. And the value of our Fy would be 345 megapascals. So, okay, solving for this is to be 4.71 times the square root of 200,000 divided by 345. So, that is to be 113.403. So, that is to be the value of this limiting factor right here. So, ano na ulit yung ating slenderness ratio? So, our slenderness ratio is 56.247. So, 56. Wait lang, KL over R is equal to 56.247. And then our answer here would be 113.403. So, if we are to compare this both values right here, would it be greater than or less than? So, by common sense, this is to be less than or equal to this. If this is to be our case, so check ulit natin yung table natin kanina. So, alin ba dito yung gagamitin natin? So, itong number 1 na to, yung nag-govern sa atin because our slenderness ratio is less than this value right here. So with that being said, for our flexural buckling stress, we would be using this formula, which is 0.658 times, 0.658 raised to Fy over Fe times Fy. So we would be using that for our FCR. So, okay. So, green na lang na naman tayo. So, for FCR, that is to be equal to 0.658. So, lagyan natin ng bracket yan. Raised to Fy over Fe. So, what would be our Fy? So, that would be 345 divided by, ano yung Fe natin? That is to be 623.923. So, 623.923. So, times Fy, which is 345. So, from that, our value of FCR would now be equal to 0.658 raised to 345 divided by 623.923. So, equal sign times 345. So, this would be our critical buckling stress. So, 273.72 megapascals. So, from that, we can actually solve for our PN already. So, lagay na natin dito red. So, for PN is equal to cross-sectional area times FCR. So, from that, PN is equal to what would be our cross-sectional area. Nalista na natin kanina, which is this. So, 9419.336. So, this is to be 9419.336 millimeter squared times FCR, and our FCR would be 273.72 megapascals. Okay, so solving for that, our value for PN would now be equal to, so 9419.336 times 273.72. So that is to be 2578260.65 newtons. Okay, so if we are to convert this into kilonewtons, so just divide this by 1,000. So divided by 1,000, that is to be 2578 kilonewton. So this is to be your nominal strength. Pero ang required sa atin would be to solve for the LRFD design strength and the allowable, the AST allowable strength. So, eto. So, it would just be like this. So, simple na lang to. So, for our LRFD, PU is equal to phi PN. So, by that, PU is equal to phi, which is 0.9 times PN, and our PN would be 2578.260 kilonewtons. So, okay, solving for that, our PU would be, so multiply lang natin to ng 0.9. So, that is to be 2320. So, 2320.43 kilonewton. So, this is to be our design strength. And as for our allowable strength, so balik tayo ng white. So, for our ASD, our allowable strength is equal to Pn over omega. So from that, PA is equal to what would be our PN. So 2578.260, 2578.260 kilonewtons. Divide it by 1.67. So 1.67. And our answer here would be, so 2578.26 divided by 1.67. Okay, so that is to be 1543.87. So 1543.87 kilonewton. So this is to be our answer for this particular problem.